Good afternoon and welcome to the Jisc Digital Media webinar, Getting to Grips with 3D. My name is Matt Faber and I am the advisor for digital imaging, digitization and 3D imaging for Jisc Digital Media. For those of you who aren't aware of Jisc Digital Media, we are part of the wider Jisc group, and our remit is to provide advice, training and guidance on all matters relating to digital media. The webinar this afternoon is an introduction to the three main technologies involved in 3D imaging, being structured light scanning, laser scanning and photogrammetry. I'll be introducing our three guest speakers who will be each speaking on their chosen topic. We will be fielding questions at the end of the webinar, so if you do have any questions throughout the webinar, then please post them in the chat room at the bottom left of the screen. And as I said, we'll be fielding those at the end of the session. I'll also be providing a slide with links to further resources for those of you who are interested. So firstly, we have Matt Ramirez, who is the lead augmented reality developer and manager at Jisc. He has previously been involved in the award-winning Scarlet project in 2011, and more recently he's been working with the Leeds College of Music developing AR solutions for student use in their music production studios. Mike Howe is the Chief Curator at the British Geological Survey and head of the National Geological Repository. He has a particular interest in promoting access to collections through digitisation and web delivery, and has pioneered the use of stereo anaglyphs and 3D digital models. His colleague Simon Harris is trained in object conservation and photography and has used these skills in the 3D Fossils project. He's currently the conservator at the British Geological Survey in Keyworth and continues to digitise parts of the collection there. And lastly, we have Stephen Gray, who's currently researching 3D imaging in cultural heritage at Bristol University's Department of Archaeology. His background is in digital conservation, and he has worked for the Tate Gallery, the Heritage Lottery Fund, and for Jisc. So firstly, may I introduce Matt Ramirez, who will be talking about structured light scanning. Thank you very much, Matt.
If you're thinking about virtual reality, it can be used to create environments. Myself, I use it within augmented reality to display concepts, animations, allow the viewer to have a more immersive feel. And also, there's various online websites where you can use your desktop PC or Mac to get a feel for the 3D object quite easily in that way. And also, lastly, I think it's really fun and engaging, and it creates a new dimension to those that have gone before it for a variety of users. So I'll be talking more about the light structure sensor 3D collection. And there's the structure sensor that I've used is available through the following website on this page. And if you want some more information, some practical applications about how it could be used, there's more demonstrations and videos on there. But basically, it's very similar to the Microsoft Kinect if you've used that before. So how it works, it records information from three different sensors. You've got your generic camera, which allows the sensor to process depth information and color view. And you've also got a third sensor. It's all infrared sensors to collect what's called surface normal view, basically which way the surface of a scanned object is pointing, whether it's the X, Y, or Z coordinate depth. And it builds the 3D geometry using a combination of all three of those things. So the color information, the depth, so how far away the camera, the sensor is from the object. And if you're able to, when we come to show a screenshot, you can actually see how the visual interface changes according to how far away the sensor is. So for very close surfaces it will be red through to far away surfaces which are blue. What it does, it actually means that you can't put it on you can't put an object on a turntable and revolve it. It uses the inbuilt gyroscope for your device. It works with both Apple and Android devices, both phone and tablets. Obviously, I'd advise the bigger the tablet, the better, really, for scanning. But it uses a gyroscope to establish the user position so that it gets a really robust scan. So, being based in Manchester and almost walking distance from the museum, I thought earlier this week, as we've got so many digital archivists and people with an interest in digital heritage, that I'd use some of the exhibits available within the prehistoric and the Egyptology section. And you can see on the screen in front of me, I've got the view which is simultaneously taken. This is a T-Rex. One from the camera view at the top, the depth view, you can see the different colours. Obviously the lighter blue colours are these surfaces that are closest to the cameras, and the surface normals. So red, blue and green depending on which way that surface is facing. And this is a view from inside the app which is attached to the sensor, so you can get information of the mesh that you've just scanned. So you can see there's a wireframe on the left-hand side and a shaded view. There's also a coloured view which enables you to, it simultaneously paints the colours. So the way this is different from photogrammetry is that it doesn't stitch a series of images together, but it processes a point cloud. So if I can zoom in, well, I can't probably zoom in, but if I use my tablet device just to annotate, I don't think I've got control of this. Yeah, so it uses a series of coordinates. So it fires 3 coordinates at various points around the image, and depending on their position, their depth, their X, Y, Z, normal view, that sort of thing, it creates a polygon, a triangular polygon. And these are stitched together to form this mesh, what you see in front of you. So you can see that there's a point cloud on the left-hand side, which is established points around the geometry, which you can see in its fully constructed view on the right-hand side. And then it uses some complex algorithms to connect the various points together, which are stitched together to form a geometry and a solid mesh. I should say that you can then export in .obj format to a variety of free software packages that you can just amend and clean up some of the geometry. This is a screenshot taken from MeshLab, which is free to download. The next, I use Blender myself, both creating and amending 3D meshes. But there's an online library which I'm sure a lot of you are aware of called Sketchfab, where you can share and download other people's scans. So this is another way of sharing what you've produced. In terms of the 3D benefits, coming back to my introductory slide, I think it allows the student to connect between the real and the virtual world. And in my job role using augmented reality, I think that's really important, having that connection there. So even if you're physically not within the museum, you have the ability to walk around the object as you would if you were physically there. It also allows for more fluid interaction for authentic learning experience. So taking theoretical applications and models and applying them to real world learning experiences. So there's that crossover between theory and practice. And I also think, in terms of trying to encourage users to visit the physical artifacts, it's a really good way of kind of getting people through the door and increasing footfall. So the way that I use 3D scans within augmented reality is in terms of using it for 3D object recognition, so using the mesh as a way of linking visualization and overlays, so that when users hold up their iPad in an AR capacity, the visual overlay is snapped to that particular geometry. And this is the way that I use it. So this is an example of a music production piece of equipment that I've scanned using light sensor structured scanning to get that geometry in place. And I've just taken that and used it as a basis and then incorporated it within my augmented reality experience using edge-based tracking. So the reason that it wouldn't work as well if I just created that model from scratch in, say, Blender, is because the accuracy down to 0.5 of a millimeter wouldn't be as specific. Therefore, some of the user experience would suffer accordingly. So I wanted the geometry to be as close as the original as possible. And in structured light scanning, although not as advanced as laser scanning, it does give you an accuracy down to 0.5 of a centimeter, which in this respect is all that you need. So that's the end of my presentation. If any of you have got any questions, I think we'll field them at the end, or any information about how I use some of the scans created via the structured light scanner. But do get in touch. There are my contact details. Thanks very much for your time.
Matt, thank you very much for that. That was really interesting. Yes, if people have questions for Matt, could they please post them in the chat room at the bottom left of the window, and we'll field those at the end of the session. Right, next speaker, we have Mike Howe and Simon Harris from the British Geological Survey. So over to you, Mike.
Okay, thanks, Matt, and many thanks for giving me the opportunity to talk to everyone today. I want to talk about a project that Jisc funded, the GB 3D Fossil Types Online project, and in particular to pick up the laser scanning part of it. I think it's an excellent case study in what you can achieve and some of the problems with laser scanning. The story really starts in 1851 with the opening of the Museum of Practical Geology in Jermyn Street in London. This was put together by the Geological Survey, and it was where they displayed most of the crown jewels in their collection. So all the important fossils, important rocks, important mineral samples were all on display to the public. Now I want to pick up in particular fossils, because for every species of fossil, there's a reference specimen, a type specimen in a collection somewhere. That's normally the one that was used when the species is described, and if at some point there's a question as to the validity of the species, or if you've got a collection of material and you think may or may not be a particular species, you need to look at the original, you need to find the type specimen. The problem is, though, that many of these types were actually defined in the 19th century, and I've stuck on the screen here a few examples from 1859, 1858, and you notice that sometimes they do give information to where the specimens are stored, Museum of the Survey or Museum of the Geological Survey, but in many cases, many publications, they might say something like the collections of the Reverend Smith, and of course 150 years later you have probably very little idea who the Reverend Smith was or what's happened to his collections. The thing is, though, that over time many of those collections have found their way into the major museums. Trying to locate where they are has been a problem. And this was the whole idea of the GB 3D Types project. It was to go through the major collections of type material in the UK and to rephotograph and to laser scan a selection of those type specimens. And just to give you one example here, of the 3 examples on the screen, the first 2 are indeed in the survey collections, which we now have here in Keyworth. The third one, though it says at the time it was in the Museum of Practical Geology, because it was an overseas specimen, that was actually one that was donated to the Natural History Museum when that opened in the 1880s. So you'd need to go to the Natural History Museum to find that. Okay, so what we've done is put a database together which feeds a website, and here's a typical example of the results of searching for Dactylioceras. Now if I go into one of these, click on the thumbnails, you can see, as on the left, you can see good high-resolution images. On the right, we've gone one better. From almost all the specimens, we have done stereo pairs. So if you happen to have any red cyan glasses or red-blue glasses and look at the picture on the right, you should see that in stereo. But, as I said, with about 2,000 of the specimens, we went one better. We laser scanned them to produce digital 3D models. And these models are also available to view on the website, or you can download them in either .ply or .obj format. And you can, in most cases, you can 3D print them, you can view them. Again, we recommend MeshLab. You can run it on an iPad, an iPhone, so you can have, if you want, your own personal 3D fossil collection. So what I want to do is tell you now a little bit about how we went about scanning them. Here's a typical example, and if you're not familiar with the sorts of results you get, here we are showing a particular bivalve, in this case, in MeshLab, and you can rotate it round. You can, in MeshLab, you can remove the texture, you can see just the underlying model, and in many cases you can actually see more detail in the model if you remove the color, if you remove the texture. And then as you zoom in, you can see the actual triangles, the polygons that the model is made of. And of course, every vertex of those polygons, they are the points, the point cloud that the laser scanner has actually captured. So the laser scanner is effectively producing a full set of X, Y, Z points in space, and each of those is associated with an RGB color. So here you are, this is a MeshLab where you have meshed up those points and colored them up according to the colors that are recorded by the scanner. So how does it work? Well, we used a Next Engine HD laser scanner. This is the scanner here, you can see on the right. It comes with a simple turntable. You can buy an optional full 3D turntable, but we found better results with the simple turntable. And again, we found it best to use twin screens and a fairly high specification PC with it. So this is the unit itself. It's small enough to put it in a briefcase and travel around with it if you wish to. It has white lights at the top and the bottom that illuminate the specimen to take color photographs, and when you're doing the initial setup, you have 2 cameras on this, and you have the laser source on the left. And as you go to scanning, this is again with a bivalve clamped in the stand, and in this case it's a set of red lines scan across it, and the device captures those and works out effectively the point cloud from that information. Supplied with this particular model is Scan Studio HD Pro software, and this is the way you work it. You see on the right a simple black and white picture that shows where the scan is going to cover, so you can adjust, you can move the supports up and down until you've got it centered. And you can make sure as you turn the turntable a full 360s that the object stays within the view of the scanner. And then on the left, you can probably see, you can set at the top left, you can determine whether you're going to do a full 360-degree scan, or just a single scan, or a bracket scan, which is a case where you do a scan of one particular direction, and then you go either side and do a scan to give you a better 3D cover. You can adjust, as you can see, the resolution, points per square inch, as either a quick low resolution, a standard, or a slower high resolution scan. You have to set the target color. It needs to know whether it's a dark or a light or a medium color. You also need to set the range, and then at the bottom it gives you an estimate as to how much memory the computer will require and how long the scan will take. So when you set it going, you first of all see a blank screen like this, and then as the scan proceeds, it starts to show you in the screen in color what you're seeing. So this is effectively the point cloud that represents the 3D model, but overlaid with the RGB color. And then as the scans proceed, you get more detail showing up on the screen. Notice in the bottom left-hand corner, you also get a monitor of a family of scans, because what happens, you would normally set it up, say if you're doing a fossil, you're trying to do a full 360, you will probably stop, well, at least 4, maybe 6, up to about 8 times. And they are grouped together as a single family, and the software will then stitch those together to give you a full model, of course missing the top and bottom where it's clamped. So here we are. We've now changed the orientation specimen. We're doing a second family of scans to try and cover those top and bottom bits that were hidden by the clamps. And you can see in the bar at the bottom that that second family is beginning to take shape. And there we are. And what you then need to do is to remove the bits of the clamp from the model. And you do this with an erasing tool. You effectively color up using the little circle or a tool you can move across the screen, color up those parts you wish to remove, press a button and they're removed. The next step now is to merge those two scans together, and you use this screen here. So you're seeing one of the scans on the left, the other scan on the right, and all you have to do is to tell the computer roughly how they align. It will do all the details, but you need to show it roughly. And to do that, you have 3 colored pins, and you simply have to drop those onto each of the models to show equivalent points. So this is often better done without the color, without the texture showing. So I've turned it off. We're looking here just at the underlying 3D model, and we'll drop the pins on. And as you drop a pin on, it actually enlarges it automatically so that you can get that positioning more precise. So here we are, one on the left, one on the right, and we've tried as far as we can to stick those red pins in equivalent pages on the model. It's quite difficult to get it exactly right. You probably won't be able to, but that doesn't actually matter. All you're trying to do is to tell the computer roughly how the two align, and it will then work out the best fit. When you've done the first 3 pins, you may be given another set of 3 to do if you wish, but it works fine without doing that. And here then is the model with those 2 scans aligned. You can then go through, if you wish, and fill in holes. You can automatically search for holes, and you can, if you wish, fill those holes. Now, we've adopted the policy that if they're just very small holes, we might automatically fill them, but certainly where there were holes of any size, we would try and do another scan to fill those holes. And if on a particular fossil it was impossible to fill the holes, then we actually considered abandoning that scan altogether. You then merge the scans, and hey presto, there is your finished model. And without the texture, without the color, that's the underlying 3D model itself. So for visualizing it, we certainly found MeshLab was particularly good. Again, as I say, a free download that you can run on a PC, Mac, and particularly on an iPad or an iPhone or Android. And you can do all sorts of things, but simply for visualizing it, it was an effective way. You could simply drag the fossil around the screen, rotate it around, see bits you couldn't see, you can enlarge it, shrink it, you can cut sections, you can measure it, a variety of things. Another program we found was Spears View. This was good, and this enables you to view it as a 3D anaglyph. So if you have, again, red cyan glasses, you can put them on at this point. And here we're looking at an ammonite, which we've now turned the color, the 3D on, and again, you can set it to rotate around automatically. I've just done some screenshots to give you a flavor of how it looks. So, laser scanning, advantages and disadvantages. Well, the Next Engine laser scanner was reasonably cheap to buy. We had looked over the past 10 or 15 years at a number of bids for funding to buy rather more expensive scanners, and were turned down. And it was only when we realized that the Next Engine was available at a price we could buy from our normal budget that we bought one, started to do the scans, and as soon as we got the scans and illustrated the grant applications, we were then successful. So the fact that we got the money to do it was really down to the ability to purchase a good quality scanner at a budget price. I have to say too that the Next Engine is very simple to operate, and it will automatically combine the textures with the model. So a lot of things that in other systems are much more complicated, it will do fairly simply. It is relatively slow, but because you can set it up on the fossil up on the turntable and then leave it to run, it can tick away for an hour or more, stopping, scanning, rotating, stopping, scanning, and so on. And then it automatically stitches those together to make one family. You then have to reposition it and repeat that. But it's quite easy for one operator to control at least 2, may even be 3 machines. And the accuracy, it's stated at 0.005 of an inch with 400 sample points per inch. That's a linear inch. We found when we tested it against much higher specification other machines at 10 times the price, that it seemed as if the Next Engine was at least as good. Although we were slightly suspicious that in some cases this was down to the software rather than the actual engineering of the machines. But certainly the accuracy is perfectly acceptable for this sort of work. Problems, well, if you've got a re-entrant area, if there's an area, a hole or something, or a crack in the fossil, it's very difficult to actually get that to reflect back to measure that point. If you have a shiny surface or metallic surface, or if you've got crystals or something, if you try and scan a crystalline mineral, certainly if it's transparent or translucent, it can be very difficult. There are ways around it. You can actually put talcum powder on a shiny surface. I've even seen a suggestion you can use athlete's foot spray, but something to take the gloss off and to give you something that the laser can actually reflect back from. We also found that if you do it in a lab with sunlight shining in, that can cause problems. The best results we've actually seen was one of our project partners who had a dark area with a wall-mounted slate slab, and the scanner, when it's placed on that, it cut out the light, it cut out the vibrations, and it gave very, very good results indeed. And finally, I should say that if you scan your fossil and perhaps set it for maybe 6 or 8 stops and scans, when it montages those images, the actual colored images together, some of those were certainly not as good as I'd hoped for. And I can understand, and you can with the Next Engine if you want, if you use a separate digital camera to take images and you stitch those together, you can actually superimpose those over the model, but clearly it's a lot more work. And for most purposes, the quality produced by the Next Engine was fine. So I'm pleased to say that last week in Vienna, the project was awarded the International Data Rescue Award. And Of course, as soon as I got it back, I passed it across to our team to scan it. And of course, the problems we had, as you might guess, it has a silver ball in the middle. That was very difficult to scan using the laser scanner. And of course, the bits between the ball and the circle, in fact, the inside of the circle, were very difficult to capture using the laser scanner. So this is one we did try photogrammetry instead and have got much better results. But that really summarizes the GB 3D fossil project, and I think gives you an idea how we use the next sensing scanner and the sorts of results we got. So again, I'm happy to answer any questions at the end. Thank you.
Mike, thank you very much for that. Absolutely fascinating, and congratulations on your award as well. Right.
Thank you.
Lastly, but certainly by no means least, Stephen Gray from Bristol University. Hello, Stephen.
Hello, Matt.
Stephen, we don't seem to be able to hear you, I'm afraid. Stephen, hello. Good afternoon to you. The floor is yours, sir. I think maybe you're having some mic problems. I certainly cannot. I can't hear you.
Can you hear me now?
Yes, I certainly can.
Okay.
Thank you.
That's great. Excellent. All right. Sorry about that. Technical issues. Yeah, we've heard about structured light scanning, and we've heard about laser scanning today. And I think I'm here to kind of make up the third way, if you like, because the project I'm going to be talking about is got a lot of photogrammetry involved with it. So the project that I'm working on at the moment has come about because of my PhD research in archaeology here at the University of Bristol, which is basically themed around having a look at 3D technologies, where they've come, how they can be applied, and then kind of handing those out to the community, if you like, rather than keeping them within the university. It's seeing what community groups can make of those and what they can do to document their own heritage. So I'm going to be talking about why 3D representations of heritage are valuable. What's the idea of crowdsourcing, in case anybody's not familiar with that? What's the kind of bigger notion about technological democratization? And then I'm going to be having a look at a concrete example, which is focusing on digitizing prehistoric landscapes. And then I'm going to be having a flight of fancy and talking about what some future possible developments which involve 3D technology taking out to communities and seeing what's possible. So firstly, I'd like to talk about why 3D representations of heritage are valuable, and I think this is a really good example. So this is a traditional tomb, thatched roof, a huge building, which was in Uganda, which was scanned by a company called SciArc using a laser scanner in 2008, and it's a really rich, detailed model. This is the same structure 2010, so unfortunately it was largely destroyed by fire, which is not exceptional considering how the thing was built, the materials it was made of. The great thing is then that the community had those 3D models of that structure. They could use the 3D information which was gathered by SciArc to rebuild this structure, and that's the case at the moment, is that it's being reconstructed. I think that's a really great example about what 3D can do for our heritage. But hang on a second, because SciArc are well funded, very well funded. So corporate funders as of 2014 include Microsoft, IBM, Iron Mountain, Autodesk, and Trimble Navigation. We're not all going to be as fortunate. Many community groups who would like to do similar things are not going to be as fortunate with their funding. So now I'd like to introduce the concept of crowdsourcing. So here's a good definition, again from Wikipedia. So crowdsourcing can involve the division of labor for tedious tasks. Split to use crowd-based outsourcing. It can apply to specific requests such as crowdfunding or broad-based competition or general search for answers or solutions. And I think this was really kind of a light bulb moment, thinking, well, maybe if communities want to record their own heritage, document, protect their own heritage, then maybe the community are the best people to achieve that. And there have been some good examples over recent years. So Old Weather is a project, a crowdsourcing project within the humanities. There have been several really strong crowdsourcing projects within environmental science and ecology. Some of them came out of Bristol and were conducted by people that I know, and they're basically themed around invasive species and mapping invasive species. And through those projects we came to learn that the quality of the output of the community, the non-professional, is often very good, extremely good in fact. So then we give everyone a £40,000 laser scanner. Well, no, not really. It's really impractical. So even where community groups are willing, we knew early on that it was going to be very impractical to give these community groups high-end, expensive technology, this is a path really which led us towards photogrammetry. So I'd like to now just talk briefly about technological democratization for people who aren't familiar with this concept. So this is the idea that we've reached a point as a species where the pace of progress is increasing as never before. Technological progress is at an all-time velocity, all-time high velocity. So combined with that is the idea that we're seeing falling costs. So for example, toy manufacturer could expect to spend around £4 million for a machine which basically creates bespoke plastic parts, or you could do this in your garage for £400, and of course you're not going to be able to make as much output with your £400 3D laser printer, but it can work. You can do that. So another important part here is the growing knowledge base. So it used to be that technological knowledge was only held by a few people. But now we're seeing kind of a trickle-down effect where the quicker technology develops, the cheaper the kit, the more the experience and knowledge which is based within communities and is outside of universities and specialist sectors. So the idea is you have technological progress, you have falling costs, and you have growing knowledge, and this all leads towards technological democratization. Okay, so now I'd like to talk specifically about a project where we're trying to put this into practice, if you like, which is, for want of a better term, 3D crowd scanning. So this can be seen as an extension of what groups such as Oxford University are doing at the moment, where they're asking amateur enthusiastic archaeologists to map hill forts. Through field walking and measurements, this is applied to hill forts, but other groups such as Heritage Together are applying it to standing stones and other kinds of monuments. It's really any kind of monument which a community feels it has ownership of, and really putting them, using their efforts, their best efforts, to document that heritage. So the project which we're embarking on at the moment uses ground-based photographs, so people walking around with cameras. It also uses aerial pictures collected using really very cheap drones, quadcopters. I think these quadcopters are around £35, and that includes a digital camera, an SD card, a charger, remote control, everything you need to be able to fly them. So in essence, these are really light things. There's very little danger in using them, and we can afford to crash a few, which happens quite a lot. So all these photographs are collected, whether it's ground-based or aerial. They're all run through photogrammetry software, which is freely available. A great solution that we've found is 123D Catch, which is online, is an Autodesk product, but is really intuitive and easy for community groups to use directly themselves. Basically, you throw lots of photographs in, and the algorithms running within the software determine what the 3D shapes must have been, which were in front of the camera, and they give you a 3D model which can be exported in many different formats. So the 3D is shared with the community group as virtual reality, and this is quite important in our research so far, is the idea that you give something back to the community. You don't simply use them to gather valuable data, you give them something back. So in this example, we've been constructing virtual reality environments and showing the community what they're like using an Oculus Rift virtual reality headset. But importantly too, this data is all going to be openly available. It's already started. We already started to put some in the public domain. So it's archived and it's shared with anyone who would like to use it. So as well as having it in formal kind of university-based archives, it's also very important to give this to the community outside of the university. So social platforms are very useful there, and the same data can be shared via social platforms like Thingiverse or SketchUp, which are used by people who have 3D printers, the Internet Archive, Flickr for images, YouTube for videos. And all of this data is available under Creative Commons licenses, so people can really use it for whatever they would like to use it for. Okay, so now comes my flight of fancy, if you like, into perhaps the future of 3D and the crowd applications. So we've already seen a couple of projects who are using looking at using motion capture to record performing arts and to pass on time-based art forms which are at risk, and that seems to be working very well. It's a very underexplored area at the moment. We've already started to see too the replication of traditional objects. So if one of the problems which affects communities is that heritage becomes dispersed due to geographical dispersion. So people go to other countries, maybe economic migrants, and they can't take the limited amount of traditional objects with them, although they would like to. So we've seen a few projects which are using 3D replication to produce copies of traditional objects. So in essence, anybody can take them away. Okay, haptics is something which is a very new area, or at least the application of haptics is a new area. So this is touch. This is three-dimensional touch, if you like. And we're already seeing some people talking about, though I haven't seen any physical application of this yet, the potential of passing on traditional skills using haptic devices. 360-degree video is already in use. In fact, YouTube are running some tests at the moment where they're going to allow users to upload 360-degree videos, and then anyone can see them using a regular desktop PC or tablet, and that seems to be working very well. And the application of that to rituals and traditional events and religious rituals is really exciting, and it's already started to be done by some of my anthropology colleagues here at the university. So then, in conclusion, I would just like to suggest that technological democratization now offers us new and underexplored opportunities, that 3D imaging need not be overly complex in order to be useful, and 3D imaging need not be expensive in order to be useful, and that communities should be encouraged to document and take ownership of their own heritage. And now that we really have reached a point where we can use 3D technology to achieve that, or rather the communities can use the 3D technologies. Okay, happy to take any questions, and thank you for your time.
Stephen, thank you so much for that. Really, really good information there. I've just moved on to the last page for this webinar. These are links to some of the 3D resources we have on the Jisc Digital Media website, including also a workshop that we'll be running in a few weeks' time in May, Introduction to 3D Digitization. We also have at the bottom of the page a link to a survey which, if you could, we would very much appreciate if you could go use that link and complete the survey. That enables us to improve our service and make Jisc Digital Media a better place for everyone. Thank you for that. Yes, if anyone has any questions, please use the chat room dialog box to put some questions across for our presenters. I will ask Matt, Michael and Stephen to remain in the session for the next 5 minutes or so they can field questions. Many thanks to all our presenters, and I hope everyone found the session interesting and illuminating. Many thanks. Ulrich, in answer to your question, this webinar has been recorded, and the link for the recording will be made available on the Jisc Digital Media website. Thank you. So we're getting a few questions now. from Maureen, any examples of using 3D digitization for political lobbying to improve environments in the community? Stephen, maybe you have something,
well, I'd like to say that I did, Matt, but no, I've no experience of that at all. But it seems like a very good idea. Maybe this could be a first. Maybe we should do that.
Well, indeed, it seems that it falls within the remit of the crowdsourcing, crowdfunding kind of arena as well. I think we have one here. If you photograph a stone circle for 3D, how many images would you require? So, sorry, I think that would be...
I think I'm having my own problems with the audio here, so I hope you can help me. Can you hear me? With regards to the stone circle, okay, great. With regards to the stone circle, well, the 123D catch software caps any item you photograph 70 photographs, so you can use 70 photographs to create one 3D mesh, and that seems to be quite good. I mean, practically, it seems like quite a good cap. So. Per item, so I would suggest that ideally per stone you would take 70 photographs, and the mesh that you get out of there would be detailed enough for most people's purposes. But of course it depends what you intend to do with your 3D model, but you'd get a good model with 70 photographs per stone.
Thanks, Stephen. Right. I see my colleague Steve has posted the link for the recording of this webinar in the chat room window there, which people can use. It'll probably I think it takes about a day or two to get the recording actually up onto the website, so please be patient with us. Yes, we're getting a little bit of a discussion going on here on other resources online to do with 3D. What is the best system to use for shiny objects? Photogrammetry? ? I think everyone would agree that photogrammetry probably is the best system for visualizing 3D objects that have highly reflective surfaces. I know that Mike was saying that they experienced a level of some problems with the laser scanner scanning reflective surfaces. So yeah.
Matt, it's Mike here. Just to say that if you haven't spotted it, Simon's posted a comment, set up with a control reflection and move the camera and not the object.
Yes, I've got that now. Yes, thank you. Also a question here. What would be the best approach for digitizing an architectural model? Whether that's a scaled model or indeed an architectural building, I'm not sure.
Personally, I think
any thoughts on that?
If you used what Stephen was referring to earlier, having a drone that was taking photographs, if it was, say, a church or cathedral on that sort of scale, and that would be the only way of getting every surface, because obviously you can't get the tops and the surfaces out of sight just by doing it from the ground level.
Indeed. I think also if it's an architectural model, a scaled model, I would suggest also, Matt, that your structure scanner would be quite a good way of approaching that as well.
If I can make a comment too, as far as the Next Engine scanner is concerned, I have seen a demonstration when they use the Next Engine scanner on a tripod photographing, in this case it was an outboard motor engine, but that's probably about the same size as a tabletop architectural model. And that worked fine. They did it in about 3 or 4 sections and then stitched the sections together. The thing, of course, you need to be careful is the resolution you're doing at, because if you stitch together 4 or 5 fairly high-resolution models, you're going to probably use more capacity than your computer can deal with.
That's really interesting, Mike. I hadn't fully appreciated that you could actually use the Next Engine in that way. Are you aware of a link so we could see the results of that scan?
I think if you go onto the Next Engine's site, if you simply Google Next Engine, they run regular webinars, and I'm not sure whether they are visible, whether you can actually see them live online, or whether you have to sign up and wait till they run it again. But certainly one of those webinars covered digitizing larger objects. So it's well worthwhile looking at the Next Engine site for their links to their webinars.
I'll have a look at that. That sounds like a really, really useful resource as well. Thank you. I think we still have a few questions coming in. Matt, Mike, and Stephen, if you need to be elsewhere, please by all means say your goodbyes. I will stay online for a short while longer to field any more questions. But thank you very much to our 3 speakers, Matt Ramirez, Michael Howe, and Stephen Gray. I hope you've all enjoyed the webinar and found the information therein useful. And we look forward maybe to seeing you again for Jisc Digital Media's next webinar, the date for which has not yet been set. But anyway, thank you very much, and all the best. Goodbye.